Why the heck I was invited to give this talk. There are many people in the audience who are much better qualified to do it than I am. I have a very idiosyncratic and sort of personal point of view about this subject, which, since someone made the mistake of asking me, I will share with you. I found two possible explanations for why I was invited. One of them is that, I'm going to talk about prospects of connecting string theory, fundamental theory to the real world. One of them is that someone finally wanted to see me give a talk that ended in less than the amount of allotted time. That's gallows humor. The other one was that someone has got to be thrown to the wolves to talk about the subject, so I'm as good a candidate for being thrown to the wolves as anyone. Anyway, but really seriously, I'm delighted to be here. And of course, string theory is so deeply interwoven with the general principles of relativity and quantum mechanics, especially after gauge gravity duality, that it's totally impossible to actually separate it from the rest of physics. And I think so much so that at the same time that it's true that in strings meetings, there are often fewer and fewer talks with anything that resembles perturbative strings in the talk. At the same time, a lot of string theorists have developed an attitude about how string theory might connect to experiment, which is much closer to the way most of the rest of physicists think about how theoretical physics can connect with experiment. If there's some kind of theoretical structure that you can understand, you think does something remarkable, you might imagine simulating in a lab somewhere, build some condensed matter system or something that actually makes it happen, and then you make it happen, you study it, you see if it does what you thought it would do, and then you go back and forth. Maybe there are surprises. It's very interesting. It's the way a lot of condensed matter physics works. And I think if you were to ask most people in this room, how will string theory make contact with the real world, that's one of the things that is probably more on everyone's mind than what I'm going to be talking about. But that's not what I'm going to be talking about. First of all, because I'm not an expert on the subject. And secondly, because it's not where my own personal interests in physics lie. I'm going to be talking about the older dream of string theory as a theory of the world, of the relativistic vacuum that we actually have with h bar c and g Newton turned on. And what the deal is with that today. So that kind of begins, how does this? Really with the picture of something like grand unification already in the 1970s. You can call it the Ming-Wei's picture of unification, that we take the seemingly complicated particle concept of the Standard Model. Already, remarkably, we see that it's embedded in a 5-bar plus 10 of SU5, further embedded into a spinner of SO10. The three coupling strengths are actually one coupling strength at extremely high energies, and if you run them down, roughly speaking, you get a picture of what the couplings we get look like at low energies. This is already a picture, even before talking about gravity, that indicated that the relevant energy scales associated with these things are going to be incredibly high. Certainly, if you're going to talk about gravity, it's obvious that the relevant energy scales are going to be very, very high, and so directly doing experiments up there was always going to be unreachable. But of course, the early hope was that there would be so many constraints on what this thing is that we'd be able to make predictions at low energies anyway. And a qualitative prediction that everyone was excited about was supersymmetry. Now, it's logically possible that the world could have been supersymmetric without strings, but it's certainly a very natural part of the whole structure. And the picture of the unification of couplings works to percent level accuracy in supersymmetric theories. And of course, supersymmetry at the weak scale stabilized, solved the hierarchy problem. It gave a plausible candidate for dark matter. And if you came to a strings conference in the year 2000 and asked people how will string theory connect with experiment, they would say this. We're going to see supersymmetry at the LHC, and et cetera, et cetera. Now, where the hell is everybody? That's the problem, right? None of that came true, right? So where the hell are Susie and WIMPs? And this is a point I'm going to, of course, come back to in the rest of the talk. But this is now around 15, 20 years ago, something that happened around the same time is that, of course, all along, there are these crushing weights on the notion of naturalness. Every idiot knew that you could say that there's something wrong with naturalness because of the cosmological constant problem. If you take the cosmological constant problem seriously, there's this orthogonal picture of the world where and then you find plausible candidates for these exponentially many vacua in string theory, mostly the universe is lethal out here, except in a few places accidentally the parameters adjust themselves to make a large macroscopic universe possible. And so maybe that's the picture. And in a sense, this is an even more extreme notion of unification. It's more impressively unified than the old Ming-Wei's picture of just, a bunch of forces here are fitting together. This is like every conceivable one of all these different possible low-energy worlds are part of one underlying structure. But of course, the Ming-Wei's hope is naively completely dead here. And I think the general attitude, whether you like it or hate it, in practice, most people's attitude about this is, well, maybe that's what's going on, actually. And if this is what's going on, the details of particle physics in our vacuum is a parochial thing. It's just some accidental consequence of where we ended up in the vacuum. Who cares about particle physics? Those things are not really deeply related to the underlying structure after all, and we should think about other things. And maybe we'll go simulate, interesting things in labs and make systems with holographic duals and so on and so forth. All right, so now I have some sympathy with this point of view, but there's also a lot of tension associated with it, and that's what I want to tell you about. One thing I should say, though, that it's always important to do experiments. And one prediction of this picture is that the cosmological constant is a constant is a constant is a constant, period. And many theorists would tell cosmologists looking to measure the CC accurately, oh, don't bother, who cares, it's so boring, we're going to get W equals -1. It's so obviously true. But thank goodness these guys, they just don't pay attention to us. They just keep going and they make measurements and they find interesting things. There's this fascinating now 5 sigma level Hubble tension, this 5% discrepancy between the measured values of Hubble in the late universe and from the CMB. And I'm not talking about it because like everyone I've tried to build models for it and they all suck and they look horrible. But it's now growing, it's not getting smaller, it's growing, and if something like this is right, I think it will completely demolish this picture, and we're just back to something much more radical and interesting going on. Okay. Now, so most of the rest of the talk is going to be about some points of view about how to think about these problems theoretically. But before I get there, I want to say a few things about the experimental frontiers. And I'll just quickly talk about the high energy frontiers, the frontier of looking for higher dimension operators and broken symmetries, as well as weakly coupled light states. So as far as high energy frontier is concerned in future colliders, I think from my point of view, the most interesting thing that's being talked about both at CERN and in China are 100-kilometer around circular colliders that could operate both as Higgs factories and eventually colliding electrons and positrons, and eventually as 100 TeV proton-proton colliders. And the central physics motivation for both of these programs is studying the hell out of the Higgs. The Higgs is strange. We've never seen anything like it before. It's an elementary spin-zero particle. It appears point-like. The very fact that it's a spin-zero particle that appears point-like is the problem. There is no discontinuous difference in the number of degrees of freedom between massless and massive spin-1 particles. That's why there's a hierarchy problem associated with the Higgs. And so from the experimental point of view, you just want to put it on under a microscope and see exactly how point-like it looks. And a Higgs factory will see how point-like a Higgs looks to external probes. For example, we'll be able to tell whether it looks more point-like to external probes by a factor of 10 more, relatively speaking, than garden variety bound states like pions do. And a 100 TeV collider will actually see whether the Higgs looks point-like to itself by measuring the triple self-interaction of the Higgs. It's an amusing fact that spin-0 and spin-2 particles are the only particle that can actually have a self-interaction where no quantum numbers of any sort change, no spin, no color, no other quantum numbers change. So it's also the simplest possible interaction you could look for, but by looking for this interaction, you're also seeing whether the Higgs actually looks point-like to itself. We won't even really know that this thing is there from the LHC, but it'll be measured to 5% accuracy at the 100 TeV collider. Another thing that a 100 TeV collider can do is settle the question of the existence of WIMP dark matter. There's a kind of a funny sentiment out there that WIMPs are dead as dark matter candidates. It's completely untrue. In fact, the very, very simplest models of WIMPs, the first ones you would have written down in 1980 or whatever, are perfectly alive and well. These simplest models are just electroweak charged particles whose neutral components of dark matter could be a doublet, it could be a triplet. The mass they have to have in order to be a thermal relic is just big. It's not your fault as a theorist. It just turns out to be 1 TeV or 3 TeV. They're too heavy to be produced at the LHC. They have tiny direct detection cross-sections, for very good reasons that the cross-section is dominated at loop level. They're extremely small, and so there's very good reasons why this very simplest model of WIMPs has not been seen yet. And I think that the most effective way of seeing this is to build a 100 TeV proton-proton collider that could actually have enough juice to directly produce electroweak particles that are this heavy. So I won't go through that slide. And of course, other things. If you thought, well, maybe supersymmetry is right around the corner, we just missed it. Well, supersymmetry can't hide at 100 TeV. You know, the sort of reach for gluinos and things like that gets up into the 20 TeV range from a 100 TeV collider. All right, there's a couple of other sort of probes of high-energy physics. One very famous one is that inflation takes place generically in the simplest models at incredibly high energies, and so there's a sense in which inflation gives us a cosmological collider. Inflationary gravity waves is the first thing that you'd want to look for, just as an indication that the energy scale was really high, and so the probe of this ratio of the gravitational to the scalar perturbations will eventually get down to about the part in 1,000 level. And we can also get possible access, as with ordinary collider physics, by looking at collisions between excitations that have large two-point functions. We similarly look for nonlinearities between the excitations in cosmology that involve the density perturbations or the inflatons, and the presence or absence of new particles can be detected from patterns in non-Gaussianities that we might see eventually. It's actually a subject I think Juan talked about at a strings meeting a number of years ago. But there's really a sort of a precise analog between looking for resonances at a collider and measuring a three-point function in cosmology and going to a particular squeeze limit of the three-point function where you begin to see oscillations, the analog of particle production in both cases. And here's a sort of window of opportunity for this parameter that's a measure of the strength of the three-point function non-Gaussianities. There's an interesting range of around sort of 4 orders of magnitude where even reasonable theories sort of populate. If once it gets down too small, you can't even in principle see it. But there is an interesting window of opportunity here that's going to be explored in the next 20, 30 years as a big part of the program of cosmology, just measuring what we know about the density perturbations in the universe. And these are very small signals, very hard to see, but remember, in principle, we're trying to probe physics at 10 to the 14 GeV. It's pretty remarkable if we could actually see from patterns of how galaxies are distributed some signal for heavy particles during inflation. What about higher dimension operators? Again, each one of these subjects I could spend hours talking about. Here I'll just take two different extremes. On the one hand, you know, the thing that we deserve the most as a gift from above is some indication for proton decay. And the hyper-K experiment is probably going to improve the limit on the proton lifetime by about a factor of 10. And then you hit a floor. Then you hit a floor where some new backgrounds come in that make it hard to see. Fortunately, we take the fourth root of this in order to get a measure on a limit on a scale, but it's still pretty good. From my point of view, the most exciting thing about higher dimension operators is in the other extreme, involving the electric dipole moment of the electron. And here there's just been incredible progress over the past half decade or so. For decades, the limit on the electric dipole moment of the electron was 10 to the minus 27 centimeters by the Cummins group at Berkeley. And then something started happening when the Acme group started getting involved, and the limit has improved by a factor of 100 in the last half decade or so, down to around 10 to the minus 29 centimeters. And they tell me that they can get to 10 to the minus 32 centimeters, another factor of 1,000 on the decade timescale. This is just mind-blowing, absolutely incredible. And just to give you an idea, you'll see an example in a moment. This is going to give us sensitivity to two-loop physics up to 100 to 1,000 TeV. Okay? So, of course, that involves CP violation, be relevant for EDMs, but still. Finally, let me say something about the weakly coupled frontier. Obviously, the most exciting weakly coupled frontier we've heard about recently are gravity waves. This is extremely exciting for astronomy. Maybe it's interesting for fundamental physics, since it's a direct probe of colliding horizons. Ordinary GR, everything is fine, you just do numerical GR. I have no idea whether if there's firewalls or something on the other side of the horizon, if it could screw some of these calculations up. Anyway, I don't know how to do that in any concrete way, but it's certainly fascinating that we get the first direct probe of colliding horizons. And there's even novel proposals for using, for example, atom interferometers in the Earth and space to look for gravitational waves. One of the real growth industries in the phenomenology over the last 10 years is people are taking a much more expansive attitude about looking for dark matter. So looking for dark matter used to be about looking for WIMPs and looking for axions, and now there's really this big range of masses when the masses are very small. You have huge occupation numbers if they're bosons, so you really think about them as dark matter waves. When the mass gets big enough, they're dark matter particles. But over this entire range, not just WIMPs and axions, there's many, many proposed experiments that are looking for these guys. And specifically for axions, if axions are dark matter, there's been a famous way to look for them for a long time, looking at the coupling of axion to photons and a resonant conversion into magnetic field, the ADMX experiment. More recently, people talked about looking for the coupling of axions to nucleons, things like varying electric dipole moments of nucleons and so on. And I think remarkably, collectively, these experiments can reasonably probe, again, asymptotically, axion decay constants up to reasonable places. String scale, they tell me even close to the Planck scale, which I think is pretty amazing if it's actually true, if the axions are dark matter. If they're not dark matter, it's harder. The axions mediate tiny, tiny long-range forces. You can try to look for experiments that pick up effectively minuscule magnetic fields. An exciting idea is that they can spin down near extremal curved black holes by superradiance. And this probes axions with an interesting decay constant with a masses comparable to the size of the black holes. All right, so that's a tour of the experimental frontier. But now I want to go back to the theoretical questions and talk about the sort of narrative that, yes, everyone expected that we would see supersymmetry at the LHC, and poof, it's not true. And so it's probably something like a landscape, in which case you can't say anything interesting about particle physics, and that's it. And the message of this part of the talk is that if you believed in the year 2000 that for sure you were going to see supersymmetry at the LHC, you were not paying enough attention to the data. And if you believe today that for sure it's dead, you're overreacting, okay? Because essentially not much has changed since the year 2000 conceptually about the status of supersymmetry, okay? Various loopholes have been closed, but the kind of spectra people were happy with that were consistent and you didn't have to stand on your head to make work in the year 2000 are the kind of spectra that are more or less on the edge of being ruled out by the LHC today. Back then, many of us were complaining that those spectra seemed funny and fine-tuned, and back then people would tell us, oh, you're overreacting, who cares, it's nothing compared to the Planck scale tuning, and so on and so forth. So anyway, there was something wrong already long ago. Supersymmetry should have been discovered at LEP, not at the LHC. It's a theory for the weak scale. And these tensions have been known for a long, long time. What was the difficulty? The difficulty, everyone knew that you should maybe question naturalness. It doesn't seem to work for the cosmological constant. The difficulty was that if you let naturalness go, then naively you lost all the things we got from supersymmetry. You lost this beautiful picture of unification of couplings and the dark matter candidates and everything. So that was the tension. The tension was that we had hints pointing in opposite directions for the status of supersymmetry, and that tension for me personally was resolved by split supersymmetry. And that's been my own picture of the world since the mid-2000s already. We just remind you what that spectrum looks like. It's a spectrum where the fermions are lighter than the scalars by about a loop factor. This is very reasonable from many top-down points of view, and also reasonable because giving the fermions mass, you also have to not just make supersymmetry, but R symmetry. Having a one-loop splitting between them is totally reasonable. The only thing wrong with this spectrum is that it's somewhat fine-tuned for electroweak symmetry breaking, but you have unification, the dark matter works just as well as before, and all of the little nagging problems of supersymmetry go away. And this picture actually made a prediction that the Higgs mass should be in a reasonably narrow window between 120 and 135 GeV, and that prediction is correct. It's not a dramatic prediction, but it could have been wrong, and it's not wrong. Okay, and it was also clear in the mid-2000s that there are sort of different pictures for what the dark matter could look like. And in fact, and since dark matter is what's motivating the bottom of the spectrum to be at accessible energies, it just depends how you have to run the picture for a dark matter. But in the very simplest way of running the picture for dark matter, I told you the bottom of the spectrum had to be at a TeV or 3 TeV. So it was already clear in the mid-2000s, if this simplest picture for the way dark matter worked was what's going on, this was not going to be accessible at the LHC. Okay, so this is well before the LHC. It is within the reach of a 100 TeV collider. Okay, so and that's the more model-independent statement. as I said, the simplest pictures of dark matter are one of the things that the 100 TeV collider should be able to settle, whether or not it has anything to do with split SUSY. There's another thing that's related to what I told you about, is the electric dipole moment, the EDM in split SUSY, is between 10 to the minus 28 and 10 to the minus 32 e-centimeters from this two-loop diagram, depending on whether the Higgsinos are light at the TeV scale or heavy with the rest of the superpartners. With maximal CP violation, this range is actually already ruled out, but with the minimal picture of split with the Higgsinos heavy, it goes down to around 10 to the minus 32 e-centimeters. Again, this is something in principle within the wheelhouse of what the future EDM experiments want to do. So, what I think is interesting is that this picture, this supersymmetric picture of the world, it's still supersymmetric, but it's a picture that would seem crazy in a mono-vacuum viewpoint of the world, but is more reasonable if you have something like a landscape. Okay, and so this is something you might imagine seeing. It will not remotely prove that something like the landscape is there, obviously, but it will be another circumstantial piece of evidence that something like that is right, and it's an example of a discovery in particle physics that could happen on the 10, 20, 30-year timescale if we actually get these machines that could actually give us an extra significant nudge in this direction. All right, now, so that's part of the reason I have a lot of sympathy for the landscape picture, but there's a lot of tensions. And I just want to mention a few things before going on to the last part of the talk. There are lots of funny clues lying around that what we see in the structure of the standard model is not just some random crap. Okay, that there is some interesting structure and not just a totally random point. Many people wonder if there's patterns in the structure of the fermion masses. Believe me, I've spent a lot of my life staring at these things, but apart from this one famous one that many people have seen, and which is somehow associated with simple textures, anyway, this is one of them that might mean something. More interesting to me are these numerological coincidences between the scale of the cosmological constant, the weak scale, and the Planck scale, and the scale of the cosmological constant and the neutrinos, and this is one of my hobby horses to keep mentioning this. This coincidence between the scale of the cosmological constant and the neutrino masses makes the following thing possible, which I think is just kind of remarkable, and I would hope means something, that the standard model itself, our world, just barely has another vacuum, which is ADS3 cross S1. If you compactify one of our dimensions on a circle, you find that the radion potential has a minimum balancing the cosmological constant, photon, graviton, and crucially the neutrino Casimir energies. You compute the size of the circle as 20 microns, the ADS3 length is 1/3 of our Hubble, and that's there. That's a solution of the world. The world has an ADS3 solution because the neutrinos are within you change the mass, you drop the neutrino masses by a factor of 2, and this is gone. Right? It's a very detailed coincidence between parameters that makes this possible. That has nothing to do with anthropics, nothing to do with the landscape selection in any obvious way. Why is this happening? Is it an accident or does it mean something? All right, so let me just spend a few minutes at the end. So essentially, with the story that I just told you around sort of 15 years ago, I, at zeroth order approximation, sort of stopped building models for a TeV scale physics. I thought this is a reasonable picture for what's going on with the world. And instead, I started thinking about what the conceptual questions are associated with making sense of the landscape. And the conceptual questions are very big ones that many of you have spent a long time thinking about. When we talk about accelerating universes, it's not even obvious what the correct quantum mechanical observables are. Everything is a little bit fuzzy. And it's clear whatever is going on with these ideas somehow has to involve not just the emergence of space, but emergence of space-time. It's cosmological. Time is very important. And exactly because we don't know how to talk about any sort of precise quantum mechanical observables in this setup, maybe even some extension of quantum mechanics is called for. This is maybe 22nd century physics. I don't know. But just to contrast with the things that we understand very well. So, or not well enough, but what we've spent 20 years understanding better and better is in the case of ADS, where the boundary observable that we're allowed to talk about in quantum gravity are just boundary correlators on the walls of the tin can. This is a case where space emerges, but the time is totally left alone. And so it gives us a great example of where space emerges from quantum mechanics. But things are, as we get closer to the real world, we lose this easy way of thinking about what the appropriate theory on the boundary should be. And one step much closer to the real world is thinking about flat space scattering processes. The world is pretty close to flat space. It's a good approximation. Of course, ultimately, the universe is cosmological. And so even on totally general grounds, if you want to think about some sort of holographic theory for flat space, even before getting to something for cosmology, which is ultimately where all the magic should be, we don't know what to do. Unlike the boundary of ADS, there's no obvious notion of time or locality on the boundary here, and so we don't know what the ab initio rules are that the S matrix has got to satisfy in order to be compatible with something that's even sort of that's causal and local in the bulk. This qualitative thing is the main reason to start thinking about scattering processes. There's a number of other reasons to think about them. Some were motivated by the hierarchy and cosmological constant problems, which are forced on us by this Wilsonian point of view about quantum field theory. And even before getting to gravity, which of course tells us that the world is not a local quantum field theory because of famous standard facts about gravity. More than that, apart from that, even in ordinary situations, ordinary quantum field theory, the whole idea of the decoupling between short distances and long distances is a deeply Euclidean idea. In Lorentzian signature, you can be very, very close to the light cone, but very, very, very far apart. And so that already hints that there are some extra consistency conditions that are intrinsically Lorentzian that tell us interesting things about quantum field theory that might not be so visible from the Euclidean point of view. And I'm not going to talk about that. That's a whole sort of very responsible program to go and try to learn. There are positivity bounds. We're seeing infinitely many new positivity bounds. There's all kinds of things we could say about that. But since this is supposed to be a crazier talk, that's what I'm talking. That's the easy part. Okay, that we'll do it. We'll be more and more responsible. We'll learn more and more infinitely many constraints on higher dimension operators. We're already surprising. There's somehow the UV is coming down and controlling the structure of the IR, vastly beyond these sort of simple statements about positivity that we made a long time ago. And I really want to return to this more fundamental question: what could the rules be? What could the rules be that govern the S matrix? I'll skip this and just say that the question is really well posed in the following sense. The amplitudes actually depend on some kinematical space. The space of physical momenta, twistor variables, the celestial sphere. These are all various ways of talking about what the boundary of Minkowski space is. But in this space, there doesn't seem to be anything obvious to do. It's not like a normal space-time with a normal notion of locality and so on, normal notion of time. So it's not obvious what question to ask in this canvas that breathes physics life into the space. And what we've been seeing over the last 10 years or so, a very tentatively emerging picture, is that indeed you have to ask strange questions in these spaces. Questions that involve combinatorics, positive geometries, forms, all kinds of funny, odd, alien things, but asked in this ordinary kinematical space. And associated with these things are new questions. We're not trying to slavishly derive causality and so on. We're trying to guess some structure that's going to give us the answer out the other end. And these objects like amplituhedra, icosahedra, even in cosmology, we're starting to see them and so on. Now, these are all things that actually describe aspects of the real world in some reasonable approximation. They expose hidden symmetries and structures. There are some hidden magic in the real world under our noses, and we can start looking for them by studying these things. These structures turn out to be deeply connected to strings in kind of somewhat more abstract ways than you might have thought of at first. They're related and generalize stringy ideas. But what I want to end with, and it'll really just be 2 minutes, the main reason I was telling you all of this is because I wanted to at least suggest that there is some potential fantasy here. And this is something I've had in the back of my mind for a long time. I think what I'm literally talking about here is a real long shot. Okay, but it's just in the spirit of this session, I wanted to mention it. See, the other motivation for thinking about scattering processes from this on-shell way is that we eliminate virtual particles. Eliminating virtual particles seems like a good idea to at least reconceptualize what fine-tuning problems are about. And it opens up the following kind of possibility, that Could it be that this new picture that we're looking for is some dual formulation of physics that represents physical amplitudes and observables in terms of some sort of funny abstract integrals over some abstract geometries, as we've seen concrete examples for in the last 10 years or now, but maybe something much more generally like this is going on. But could it be in such a formulation that things like the cosmological constant and the Higgs mass are obviously exponentially small? So if you begin with this picture, it's obvious that the answer is exponentially small, but it's not obviously corresponding to local physics. And something that we've seen in these examples is that, indeed, you have these abstract objects, and one presentation of them, one triangulation of them, and so on, makes Feynman diagrams manifest. Other ones make the hidden symmetries and other things manifest. So could it be similarly here? There's another formulation that breaks this obviously tiny answer into different pieces so that it appears fine-tuned, different pieces with different number theoretic content, so that the final answer appears fine-tuned when expressed as in standard local Feynman integral, in standard local quantum field theoretic terms, but is manifestly tiny when you think about it in the original language. And I'm not going to go through this since David is threateningly standing up there, but you can see it in the slides, and I'm happy to talk about it afterwards. There are some toy examples of this phenomenon that we've been discussing with my friend Yuval Grossman that indeed involve this idea of connecting tuning and transcendentality and sort of concrete examples. In fact, there's some amusing examples already sitting there in ordinary quantum field theory calculations of strange numbers like pi squared minus 9 popping out of calculations that are mysteriously small. And it's not an accident. There's a mechanism at work that makes these interesting cancellations between transcendental and rational numbers. And it's very much a realization of this sort of general thought that there's some object. So here's a concrete object, which there's no big or small numbers in this concrete object. It doesn't look like a quantum field theory calculation. But for good, simple reasons, when you try to express the final answer, it's forced to come out to look like a piece that looks like a one-loop Coleman-Weinberg calculation and a bunch of rational pieces that look like something that's sitting there at tree level already, such that there's guaranteed to be a massive fine-tuning between the two of them to make the Higgs mass very small. This is sort of a concrete example of a fine-tuning coming out of such a different underlying formulation for simple number-theoretic reasons. That has exactly the sort of flavor of this fantasy that I was talking about. It even makes a rough experimental prediction that we see in these examples that when such a sort of tuning mechanism is going on, you see there's much more fine-tuning than you naively need. Not just the Higgs mass turns out to be tuned, but many higher dimension operators are tuned as well. And that's actually an interesting opportunity to look for experimentally. If you see that also a bunch of higher dimension operators are finely tuned, there's clearly nothing anthropic going on. There's some different tuning mechanism or something different going on. All right, that's it. Maybe I'll just end with one comment that if you want to connect fundamental theory to the real world, you should think about the real world. And the reason is not what sort of armchair philosophers of science say. The armchair reason is that, well, we need experiment to decide what ideas are right and what ideas are wrong. I mean, that's true. At a sort of trivial level, it's true. But for such a grand structure as string theory, it's also basically irrelevant for the reasons that most of us know. For me, the main reason to think about the real world is different. I mean, of course, if we have reams of data, it's a separate story. But in the kind of situation we're in, the reason to think about questions about the actual real world around us is more fundamentally creative. It's because the real world knows much more about theoretical physics than theoretical physicists do. And the real world is better at posing interesting problems that sort of force you out of your theoretical comfort zone to discovering new things than just sort of iterating around all the things that you've understood and gradually growing the large continent of theoretical physics. All right, thank you very much. I told you I wouldn't end early. I told you I wouldn't end early.
The reason you were asked was not to see you go only 10 minutes over time.
Oh, my goodness.
So it's interesting, there were very few questions about the real world. There were questions for you, Nima, and I promised to relate the one that contained the word God.
Yeah, I would love to hear that one, yes.
So here we are.
Just don't offend my hardcore Shiite Muslim sensibilities.
Not at all.
Be very careful. Be very careful. Yeah.
I think you've answered this already, actually.
Yeah.
Do you really believe that God has written the world, and parentheses, and also speaks to you, in the language of polytopes?
No. Definitely not. No, no, no. Excellent question, though. But God does speak the language of polytopes, but let me say, actually, I don't know.
God does speak.
God certainly speaks language. God speaks all kinds of
yes,
things. No,
but
the
he
thing is
doesn't
that
speak to you directly.
no, unfortunately, he doesn't speak to me directly. And if he did, I wish it would be something I could understand better. I mean, I suck at all of these things, you know. So I wish it was something I was actually good at. You know, I'm not good at any of this.
There was one more question to you. Again, not so much about future colliders or things, but rather, which is kind of interesting. Is it possible to repackage the infinite number of crossing relations, the bootstrap, if you want, at every space-time point in a more elegant, analytically amenable construction, a la amplidehedron?
Right. Well, so I think this is a great question, and maybe I'll answer something slightly broader. So we can ask, how are these things different than the old S-matrix program that you know everything about? And the answer is, and it's really interesting
it's
to also—
similar in the sense that it probably won't work.
Well, so it's similar in the sense that, I mean, polemics aside, it's similar in the sense, obviously we're talking about the same observable. And it's also interesting to contrast this with the conformal bootstrap. Okay, so let's talk about the S-matrix bootstrap first. Why did the S-matrix bootstrap fail? Because people thought they would be able to discover what the principles were, analyticity, essentially analyticity, to control how causality is reflected in the S-matrix. That's the big question, right? You have a boundary observable. How the hell do you know that what happened was something even roughly that looked local on the inside of the space-time, when one particle hit the other and all the rest of it? And they somehow thought they would be able to slavishly derive it from the top down, and they failed. And the reason for it is not even all that technical in the end. You see it, if you talk about even simpler processes involving massless particles, you see that this entire philosophy, that the analytic structure is going to be controlled by physical processes in Minkowski spacetime that you're going to control with unitarity, has to be wrong, because you can't even access all of the interesting Mandelstam invariants where the singularities happen in Minkowski spacetime. Okay, so that's the sort of basic reason why this whole program was doomed to begin with, to try and derive from the top down, from ordinary physical principles, what the rules are. See, it has everything to do with the fact that it's on shell and Lorentzian and time dependent. So in the year 2019, we do not know the rules. You hand me an S-matrix, I don't know precisely how to check if it's right or wrong. In the real world, simple things, we know the answer for conformal theories. Euclidean conformal field theories, we know the answer because it's Euclidean. And because it's Euclidean, all these subtleties about the important subtleties about the Lorentzian physics go away. So what's new? What's new is that instead of imagining we're going to slavishly derive it from the top down, the hope is that we're going to discover structures that just give us the answer. So that's the essential difference, is turning the problem on its head and trying to look in the kinematic space, look in the space where these amplitudes live, for a natural question. Now, it's inevitable the question is going to look a little alien and a little weird, just because it doesn't have all the things we're used to talking about in physics. And maybe it's all a mirage, and none of it will really go anywhere beyond the few examples that we've seen. But there are a few examples where it's not that it's packaging what we knew from unitarity. It's a completely different question that gives you an answer that you then interpret the pieces as being associated with unitarity and causality and locality. That's the hope. That is the hope and the dream. And the hope and the dream is that if we actually figured out what such structures look like, we'd have a more coherent picture of UV completion, gravity, all the rest of it, beginning in flat space, and ultimately in cosmology, where all of the magic really should be.
Okay, we're going to have now a coffee break, and we come back when? In half an hour? What? At 4 o'clock. Coffee is served.